This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Next speaker is Carolyn Wood from the University of Queensland, and she's speaking about quantum kernel learning for bosonic modes.
Thank you, and thanks to the organisers for having me speak, and to all of you, of course, for being in the room. Now, I know not everyone here is a kernel expert, so I hope I've included just enough details to satisfy everyone. But I guess some of the current open questions we might be thinking of are universal to quantum machine learning. Namely, when do quantum computers actually become the most useful for machine learning tasks? And in the case of kernels, we also wonder how we find useful kernels for quantum machine learning. Should we take an approach where we're looking for kernels that can be useful for the most problems, or should we be designing or finding kernels that are suited to the task at hand? And it's possible that the answer to both these questions could be related to where computational complexity lies. So basically I'm saying quantum utility may be reached when a problem becomes too hard for a classical computer. So this will be my main word on kernels in general. As a quantum physicist, I quite like kernels because of this analogy between how kernels can access multidimensional feature spaces and how we say quantum states exist in multidimensional Hilbert spaces. So in this case, we can say that the kernel is just the inner product of some encoding quantum state. Now, a lot of people, of course, work with qubits. Maybe not so many work with continuous variables. So as you may know from the title, I'm working with continuous variables. And as we heard from Jens on Tuesday, a lot of quantum systems are natively in the continuous variable realm, so why not exploit that property? However, because they work in these infinite dimensional spaces, they're hard to simulate. So we took inspiration from this idea of universal continuous variable quantum computing, where about 20 years ago, Seth Lloyd and Stephen Brownstein suggested that if we have a state that suits this algebra for universal simulation of a bosonic mode, then we should be able to get away free. So the A's there are just creation and annihilation operators, because we're talking about bosonic modes. The first two terms generate displacements of the quantum state. The next two generate squeezing. So they correspond, if you're familiar with Wigner functions, to the coherent and squeezed states. And then the fifth term is related to a Kerr nonlinearity, which is a property that arose in optics originally, where the strength of the nonlinearity is photon number dependent. So a Kerr nonlinearity can correspond to a Schrödinger cat state. So in these Wigner functions here, the coherent and squeezed states, the top two, the quasi-probabilities, which is the z-axis there, are entirely positive. So they're often called semi-classical states because they're sort of as classical as you can get. The Schrödinger cat state, on the other hand, has some region of negative quasi-probability. So then we start to think, well, this is a undeniably quantum state here. We can't really say it's semi-classical anymore. So the idea is that maybe Wigner negativity is the key to the complexity or the quantumness that we might be looking for to find problems that are too hard for a classical computer to tackle. So I'm going to immediately give you equations related to a two-mode coherent state with a Kerr nonlinearity, because that's what I'm going to be using for the rest of the talk. So we've got the interaction Hamiltonian there, where we've got a self-Kerr term for each of the modes, and then this cross-Kerr nonlinearity generates entanglement between those two modes. So we have this encoding state here, a two-mode coherent state with a cross-Kerr nonlinearity, where I've already put x and x2 there because that's where I'm going to place my classical data when I encode. So casting that same state into the number basis, it looks like this, and from that we get the kernel, which looks like this. Now, the idea here is that if we use a platform that's natively quantum natively continuous variable, we could potentially do our whole machine learning pipeline in a lab, say on an optical system or a superconducting circuit system. Because then we can exploit that infinite dimensional space without having to deal with it. Now, I've dangled that carrot in front of you, and I'm going to immediately snatch it away because that's not what I'm going to be talking about for the rest of the talk. I'm going to be benchmarking this kernel on my classical laptop, which means I have to deal with this infinity here and truncate my Hilbert space to make that tractable. Sort of the exact thing I'm saying that we want to move away from. So I don't have a nice cat picture to break up the two sections of the talk, but here are the two questions I want to answer today. So firstly, can a CV quantum kernel with a cross-Kerr nonlinearity learn? And secondly, how does it compare with learning of standard classical kernels? So for my algorithm that I'm going to use for this test, I'm choosing a support vector machine, and that will basically be a binary classification task. If you're not familiar with the support vector machine, it's basically uses the kernel to find a linear separating hyperplane in multidimensional feature space to classify two categories either side of that plane. And it's called a support vector machine because the plane can be reconstructed by a minimum amount of support vectors. Okay, so I start by generating some random real numbers on the unit square, and then I encode those into that quantum state I showed you just before. And then I measure via a displaced parity operator to get some labels. So that effectively gives us this originally flat classical data, or 2D classical data, separated in space, and everything above the 0 line I give a label of +1, and everything below I give a label of -1. You might think that's highly contrived, but remember, this is multi-dimensional, not just the dimensions we see in my plot there. And you might also think it looks a bit like a Wigner function. You would be right. It is a Wigner function, but evaluated at whatever I choose as my mu and nu displacement operators. So depending on my different values of mu's and nu's, I can generate different mappings or different labelings for the same original classical data set. So we put that into our support vector machine. I took a training set of 3,500 data points, loaded into the support vector classifier in scikit-learn with my custom Kerr kernel. And these are the simple accuracy and precision results. They're pretty good. And if you're familiar with confusion matrices, you'll see here that my false positives and negatives are quite low and quite balanced, which is good. And you'll note also that I've got far more positive labels than I do negative labels. Now that's because that Wigner function has far more positive space than negative space. However, because this learning is reasonably good and this part here is balanced, we're not worried about that being biased by one label over the other. So then for my classical comparator, I had the radial basis function, which is a Gaussian, so seemed like a fairly robust choice to compare. And I performed that test twice, first without tuning hyperparameters and then after tuning hyperparameters. You'll see the numbers came up quite a bit by doing that. And it starts, with tuning, it starts to approach the accuracy of the Kerr kernel. Right. And if you were following my algebra earlier, you might think, oh, what about the squeeze state terms? Well, we did also look at squeeze states. It's just they're much harder computationally, so they take 12 days to run on my computer. So I haven't included them yet. But we have similar results, but we now have this extra dimension of the effect of the squeezing. And as you can see there, whether it's positive or negative alone changes the bumpiness of the state. Right, so I think I've breezed through that incredibly fast. Returning to my two questions I wanted to answer, can the Kerr kernel learn? Yes, it can. And it actually outperforms the classical kernel just out of the box with no hyperparameter tuning. So in the future, it's really important that we look at the effects of dissipation in this for this kernel. If we want to move into the lab and use these actual quantum systems, that will be imperative. And then we're looking at actually doing those experiments in the lab, for example, with superconducting circuits. So we have some notes on the archive if you'd like to check them out, and I'd like to acknowledge my co-authors, Sally, who's in the room, I believe, and Jared, who some of you may know. Thank you.
All right, questions? Yeah, over there. Michael? Oh, okay, Ben. Yeah.
So you were saying that in your simulations you're truncating the basis of the bosonic modes. I guess that just limits the number of photons that you can include.
Yep.
What do you think you're losing by making that truncation?
I'm losing my argument that I'm using a continuous variable system, essentially. So I believe I truncated that sum to 10 because that ran for 90 minutes on my computer, and that's pretty good. Basically, if you just look at the average photon number and you make sure your dimensions are bigger than that, you're okay for the purposes of this test. That's not what we want in the end, though. Yeah. And for the squeeze state, you need even more terms in the sum because you've got more photons from the squeezing.
Okay. Any other question? We would have time for one more. Yeah, over there, Ben. There.
So I've always been deeply skeptical about quantum kernel methods. Just kidding.
Cool.
No, all joking aside, one of my concerns has always been the fact that, unlike classical kernels, right, these methods don't really give you any advantage between distinguishing between quantum state vectors that are on two sides of a narrow gap between the concept classes in your geometric space. And because of the fact that you run into these state discrimination bounds, kernel methods, can run into computational complexity issues for classifying anything. So I was just kind of curious if you spent some time taking a look at these issues, and also what the complexity would be if you wanted to go through and actually do these classifications on a quantum computer that you simulated.
I have not looked into that, but I'd be very interested in looking into that. However, I do suspect that many others are a bit ahead of me on that road. I snuck in a citation at the bottom of one of my slides. Oh, I can go back to it. Colleagues from my group, at the bottom there, Laura's paper, which she had a poster on yesterday, looks into the stellar rank hierarchy, which it's not directly addressing the complexity issue, but it's starting to sort of join up with that research. So yeah, it's something I think we may look into in the future. Thanks.
All right, let's move to the next speaker. Okay.